Hello, welcome to our video on light waves. We've kind of not really talked about light waves all that much. We briefly touched on them once when we were talking about wave characteristics, but we've stayed away, and the reason that we've done that is because light waves are very different from other types of waves. They still have frequency, they still have speed, they still have a wavelength, all that stuff. They still have an amplitude, but they're just different. There's something about light waves that they're just different enough that we focused more on mechanical waves first. I guess the main reason that light waves are different is because of how they're formed. A fancy word for light waves, or all the different types of light waves, is the electromagnetic spectrum. The electromagnetic spectrum, you see that first word, electromagnetic, has two words in there that you recognize. Electro, meaning electric, magnetic, meaning obviously magnets, and then spectrum just means a range of something. The electromagnetic spectrum consists of all the waves that are created by variances of electric and magnetic fields. That's all a light wave is. It is a set of electric and magnetic fields that are changing in such a way that it's a wave, actually. So these variances, or light itself, are created by accelerating charges. And we know what charges are. We mean electric charges here. We mean protons and electrons. That's the foundation of all different types of electromagnetic waves, which we refer to colloquially as light waves. So what's happening here? If you look at this picture, we have two different components here. We have this kind of vertical, kind of sine wave looking thing, and we have this kind of horizontal one that's kind of at this angle here. Now, the vertical one is labeled as an electric field, and then this is labeled as a magnetic field. What this is showing us is the change in the electric and magnetic fields that happen due to light. If you could take a light wave and kind of stretch it out and see why it's a light wave, what you would see is along this path, the light wave is traveling in this direction, you would actually see variances in the electric field along this path and variances in the magnetic field. And these variances happen at such a rate and in such an amount of space that gives the light its characteristics. Light is just a combined set of varying electric and magnetic fields. And obviously, if you remember, light travels extremely fast. So these variances move along the direction of light very, very quickly. We're talking like millions and billions of times per second is how frequently these electric fields and magnetic fields change. If you remind me, I'll tell you the story about when we first discovered in college, or when we were first taught about light being a set of electric and magnetic waves. It's kind of a funny story. So, in your reference tables, we are now looking at the reference tables page 2. Okay, we have not looked at this page ever before. Page 2, at the top, there is a chart called the electromagnetic spectrum right here, and that is given also right down here. The electromagnetic spectrum is a picture, a chart of every different type of electromagnetic wave that you might encounter this year. So we have down on the right-hand side, I'm going to read from right to left right now, we have radio waves, and actually all of these are different types of radio waves, long radio waves, AM, TV, and FM. Those are all, excuse me, those are all considered radio waves. Then we have microwaves, we have infrared waves, we have this tiny little patch, a tiny little area here that is visible light. We have ultraviolet light, X-rays, and then gamma rays. I want you to really focus on the fact that visible light, this is the stuff that we see. When you think of light, you are thinking of visible light in all of its colors. Red, orange, yellow, green, blue, violet. Okay, that's everything that we can see. Brown and black and white and gray, those are just combinations of those. And all the colors that we can see are contained somewhere within in this chunk right here. Look at how big that is compared to the electromagnetic spectrum. It's tiny. It is absolutely tiny. It takes up a tiny portion of this chart. Okay? I would say like 1/100th of the chart, but then you look and this is a logarithmic chart, meaning it's not a set amount each time, that like the tick marks on the chart. It goes from, so here's 10 to the 0, that means 1, 10, 100, 1,000, 10,000. 0.1, 0.01, 0.001, 0.0001. This is not a logarithmic chart. Okay, it's based on these exponents here. That's how big. That's how these how widely different types of electromagnetic waves can vary. Light is just a tiny, tiny portion of this. Another thing that I need you to know right now is I need you to look at these axes. There's not a vertical axis for this chart. It's simply two different horizontal axes. I want you to look at the frequency. We have 10 to the 21st frequency right here, and it goes all the way down to 10 to the 5th up here, or down here. So the frequency on this chart increases going to the left. The wavelength, on the other hand, starts at 10 to the negative 13th and increases going to the right up to 10 to the 4th. This kind of makes sense. We know from the equation V equals F lambda that frequency and wavelength are inversely related for waves in a certain material. So notice that the frequency and the wavelength are inversely related. In other words, the larger the frequency, the smaller the wavelength gets, and vice versa. You need to become a pro at reading this chart. And we're going to practice a lot, but you really need to focus on reading this chart. This has a lot of information in it. Before we get to looking exactly at what's going on here, let's talk about the speed of light. In a vacuum, which we've defined as just being empty space, a lack of any solids, liquids, or gases, light has a certain speed that it travels at. It's on the front of the reference tables. It's one of the most important numbers in physics. Speed of light in a vacuum, symbol is c, I think it means c for constant, 3.00 times 10 to the 8th meters per second. We've seen that before, but we're going to write it again. C equals 3 times 10 to the 8th meters per second. This is an important number because you can refer to it as the speed limit of the universe. No object can physically move faster than this. Now, this is usually the part of class where I start to get a lot of what about questions. You know, what about this? What about this? I'm going to stop you there. It is the speed limit of the universe. No method that we currently know about can allow objects to travel faster than 3 times 10 to the 8th meters per second. Are there some things that we're working on that are really, really complex that might mean the speed can, or that objects can get from one place to another faster than light can? Possibly. But the speed limit of the universe, no object can move faster than this. I should say no object other than that has mass. Light moves this fast through a vacuum. Okay? That is the only thing that can move this fast. Any object with mass cannot. You might be saying, well, what if we just put a really big force on it? What if we get lots of energy? Trust me, this is an intro course. There's some stuff that you are not aware of yet. It is impossible for objects to travel this fast, okay? If you're interested in it, I'm happy to take your questions, but I just have to warn you that there's no answer that you are going to like, okay? Objects cannot travel this fast. As a matter of fact, if you want to read a little bit about it, I would suggest a good intro book on relativity, maybe something by Stephen Hawking. Okay? It is really interesting. I'd be happy to talk with you about it, but that is the rule that we are going with for right now. That's the speed of light in empty space, in a vacuum. In other media, which is media is just the plural of medium, in other media, light travels slower. Typically travels slowest in very dense materials or medium. For example, in water, light travels at only, I say only because it's still super fast, 2.25 times 10 to the 8th meters per second. Okay, that's a 25% reduction in speed. And again, remember, the speed of a wave is only dependent on what material it's traveling through. Changing the frequency and wavelength does nothing to a speed. The speed is solely dependent on the medium. That is a fact that you have to know. Let's practice a little bit with the frequency and wavelength table, the electromagnetic spectrum table, and these questions. All of these are questions that you might get on a Regents exam. If we're comparing between infrared, visible light, and radio waves, which waves have the highest frequencies? Remember, frequency goes up as we go to the left. It's 10 to the 5th down here, 10 to the 21st. It must increase going to the left. So infrared, visible light, and radio waves. So let's see, radio waves are over here, infrared is over here, that has higher frequency than radio waves. Visible light is defined as having a higher frequency than infrared. The answer must be visible light. Okay? Don't get tricked and think that frequency goes up this way. That's wavelength. Wavelength increases to the right. Matter of fact, between infrared, visible light, and radio waves, which waves have the largest wavelengths? Again, here's visible light, kind of near 10 to the negative sixth. Infrared goes up to 10 to the negative third. That's bigger than 10 to the negative sixth. Think about it, or write it out if you need to. Radio waves go from about 10 to the negative 2, 10 to the negative first, all the way up and basically infinitely long, 10 to the fourth and above. Radio waves have the largest wavelengths. That also means they have the lowest frequencies because they're inverses of each other. By the way, radio waves are not the same as sound waves, and we'll talk about that in a little bit. Which has a higher frequency, violet light or red light? Visible light is right in here. Violet is over here. It goes up to 7.69 times 10 to the 14th. Red light goes up to 4.82 times 10 to the 14th. Those are frequencies, so higher frequency must be violet light. By the way, how to read this chart right here for visible light? These are like the boundaries for violet light, okay? Light that we would call violet is between 6.59 times 10 to the 14th and 7.69 times 10 to the 14th. Violet light is considered, those are the boundaries, okay? And it's not all like the same exact hue of violet light. You're gonna have something slowly changing from like a very bluey violet to very, very purple, okay? So purple you can almost not see it. The boundaries for blue, 6.1 times 10 to the 14th up to 6.59 times 10 to the 14th. Those are all the different shades of blue. Here's all the different shades of green, all the different shades of yellow, all the different shades of orange, and all the different shades of red. Down here is the base of what we can perceive with our eyes as visible light, 3.84 times 10 to the 14th. That's basically almost, and it's going to sound silly to say it, it's so red you can almost not see it. Which has the larger wavelength, violet light or red light? Well, if violet light's got the highest frequency, that means it's also got the shortest wavelength. Red must have, therefore, the lower frequencies and therefore a longer wavelength. By the way, I want to make this point right now. It's very easy if you're asked, oh, here's a frequency of light, what color is it? You just go in this chart and you say, okay, well, let's say it's 5.8 times 10 to the 14th. That is between these two numbers, so that must be green. If you're given a wavelength of light, my extremely, I need you to do this. This is a huge recommendation. You absolutely need to do this. If you are given a wavelength of light, it is, and it could be any type of light. It could be anywhere on the spectrum. It is going to be much easier for you to read this chart and to figure out what type of radiation it is if you first figure out the frequency. Now, how do you do that? Well, if you know the wavelength, then it's a good bet that you also know the speed, because probably this question is saying it's light that's in a vacuum. Okay, so if you know the wavelength and you know the speed, you can find the frequency by using V equals F lambda. Even if you don't know the frequency of light, or if you don't know what material it's in, it's not that hard to figure it out. If you know that it's not in a vacuum, you can still figure out what the speed is. And we'll talk about how to do that in the next video. But it's going to be much easier for you to determine what type of light you're dealing with if you figure out the frequency and you use the wavelength to figure out the frequency. Otherwise, what happens here, since you're given all these frequencies of light, what if you're given a wavelength of about something times 10 to the negative sixth? Depending on what the actual type of light is, it could be something kind of like infrared light, it could be visible light, or it could be ultraviolet light if you're given a wavelength of about 10 to the negative 6 meters. However, if you convert that to frequencies, you can easily see if it's visible light. If it's lower than this number, then it's got to be infrared light. If it's higher than this number, it's got to be ultraviolet light as far as the frequencies go. So I can't recommend this enough. I need you to do this. If you're given a wavelength of light and you're asked what type of light it is, figure out what the frequency is and use this chart. Finally, last part on the front, which type of waves would have wavelengths that are about the size of a human's height? Humans are approximately, well, let's see, think about a meter stick. I'd say most humans are somewhere between 1 and 2 meter sticks tall. That would be 1 to 2 meters. So we go on the chart and we look for wavelengths that are about 1 to 2 meters. 10 to the first, let's see, that would be 10 meters. It's got to be lower than that. 10 to the second is 100. Oh, we're going the wrong way. 10 to the 0 is 1, so somewhere between 1 and 10. Okay, so that means TV or FM and just in general radio waves. Microwaves probably a little bit too small unless we're talking about a really small child. Okay, 10 to the negative first, that would be 0.1 meters. That's like 10 centimeters. That's way too small. So I'd say radio waves slash TV slash FM waves. Okay, so again, you have to get good at reading this chart. You're going to get lots of practice with that. On the back, we are just going to learn a little bit about each different type of electromagnetic radiation, all the different types from that chart. So it would be a good idea to keep that chart out with you so you can follow along and see what I'm talking about. Remember, all electromagnetic waves, regardless of their wavelength, regardless of their frequency, move through empty space, a vacuum, at a rate of 3 times 10 to the 8th meters per second, and the symbol for that is lowercase c. Different types of electromagnetic waves, that's the abbreviation EM, you can also call them different types of radiation. Okay. They have different frequencies, they have different periods, they have different wavelengths, and they have different amounts of energy. Okay, and before we begin, we're going to keep referring back to this chart on page 2 of the reference tables right here. See how these ranges overlap? So you might be saying, how can something be both a microwave and a radio wave? That's fine. The reason that there's two different types is because of how the waves themselves are generated. Radio waves are generated in a different way than microwaves. So just a quick note, the ranges can overlap. The waves are classified based on how the waves are created, or generated is a better word, based on how they're generated, okay? Remember, at the principle, all these waves are generated, they all are composed of changing electric and magnetic fields, a set of oscillating or, vibrating back and forth electric and magnetic fields. Like literally the electric field strength is increasing and decreasing in the form of a sine wave. Same thing with the magnetic field, okay? We don't have to know too much about that. You just need to know that electromagnetic radiation is caused by changing electric and magnetic fields. We're going to start with radio waves. Remember that radio waves are all the way down here on the right-hand side. They also include TV and FM, AM, and these long radio waves. These are waves with low frequencies and high and long wavelengths. So these have long wavelengths. They have low frequencies. If they have a low frequency, frequency and period are also inverses. So that must mean that their periods are long, meaning it takes a long time for one wave cycle to happen. And we'll also see that they have low energy. Radio waves do not carry a lot of energy with them. The frequency range for radio waves seems to be lower than about 10 to the 10th hertz. So I'm going to do less than, nope, that's not the less than sign, less than 10 to the 10th hertz. Remember, hertz is the unit for wave or for frequency. Their wavelength range is greater than approximately 10 to the negative second meters. 10 to the negative second is a centimeter. My pinky is about a centimeter in width. Radio waves, the smallest radio wave, okay, still has a wavelength of about my pinky. These are generally big waves that you can see, and it really reinforces how small the other types of waves are. Again, this includes radio waves. It includes the waves that help your television run, and it also includes FM and AM. They're two different types of radio, those waves. They are produced by charges accelerating through a wire, okay? Car antennas or old TV antennas, they work because they would detect radio waves, and those radio waves would cause charges in those big, long metal sticks, for lack of a better word, essentially wires, to accelerate up and down. Remember, light is made up of electric and magnetic fields. A charge responding to an electric field is going to feel a force. It's going to accelerate up or down. Now, I'm not an expert in exactly how it works, but that is what causes you to be able to get some sort of signal on your radio or your TV. It takes those charges moving in the antenna, and it creates a picture out of them, or creates sound waves out of them. And I want to be very clear, radio waves are not the same thing as sound waves. Sound waves are longitudinal. All electromagnetic waves are transverse waves. Okay, all these different types of waves, because they can move through a vacuum, they can move through empty space, they must be electromagnetic waves, and they are also transverse waves. Remember, transverse looks like this. Can you see this? No, you can't. Transverse waves look like this. Okay, that's a transverse wave. The stuff that comes out of your radio are sound waves. What you are hearing are sound waves. Those sound waves are coming out because the radio is detecting radio waves and then converting those through some process into sound waves. All right, microwaves. Those are the next. Microwaves have higher frequency and smaller wavelengths. Their frequencies are anywhere from 10 to the 8th up to about 10 to the 13th hertz. Okay, so a little bit more. They can have a bigger frequency. Their wavelength range is anywhere from about 10 to the -4th meters down to 10 to the 0th power meters. Microwaves are typically used in communication systems, in air and space, they're also used, as you are familiar with, to cook food. Okay? The reason that they can cook food, certain molecules in food, typically water molecules, have natural frequencies. Remember, a natural frequency is the frequency that an object will vibrate at, that are similar to frequencies produced by a microwave. So a microwave produces this type of electromagnetic radiation. When it hits the food, it causes the food molecules to wiggle, or if you want to be a little bit more specific, causes them to resonate. They kind of jiggle around in the food, and as they're jiggling around, they knock into other things. They cause them to move faster. So we're increasing the kinetic energy of all these particles. And if you remember from chemistry, kinetic energy of a gas we see as temperature. So this creates heat. It heats the objects up. That's what a microwave is. Infrared waves, right here. Bigger frequency, lower wavelength than microwaves. Frequency range is 10 to the 11th up to about 3 times 10 to the 14th hertz. Okay, probably a little higher than it actually, about 3.84 times 10 to the 14th hertz. Let's focus that, because that's the lower bound of red. The wavelength range is anywhere from 10 to the -6th up to 10 to the -2nd meters. Infrared waves are given off by warm objects. Okay, this is how heat vision or night vision goggles work. Okay, any warm object, or really most objects, give off infrared waves. It doesn't even have to be particularly warm. They give off energy in the form of radiation, and usually it's in the form of infrared waves. So these are used for heating, and they are also the principle behind night vision goggles. Night vision or heat-seeking goggles, they sense the heat coming off an object, and they just convert those infrared waves that they're picking up into a picture, a visible light picture that you can see. Those are infrared waves. Now let's get to visible light. I'm not going to talk too much about these because you already know way too much about visible light. It's all you see. The frequency range is from the lowest red to the lowest frequency red up to the highest frequency violet, approximately 3 times 10 to the 14th hertz, up to 8 times 10 to the 14th hertz. The wavelength range is anywhere from approximately 3.75 times 10 to the -7th, up to 1 times 10 to the -6th meters. Now, everything that you see, that you've ever seen before, every color, is visible light. It's a tiny fraction of the spectrum. It's crazy to me that that's how it works. We have very special cells in our eyes. They register this light. If you ever take a course on it, you might talk about rods and cones and all this stuff, and our brain converts it into usable signals. Our brain detects just these frequencies of light, or our eyes detect it. They send this information to our brains, and our brains interpret it and create a picture for us so that we can see. It is crazy to me that when we see colors, we are literally just seeing light bouncing into our eyes at these frequencies. That is nuts to me. That is so cool. 3 more types to go. Ultraviolet. Notice infrared. Infra basically means below red. Ultraviolet means above violet. We're talking about the frequencies there. The frequency range for ultraviolet is 8 times 10 to the 14th, up to 10 to the 18th hertz. The wavelength range is anywhere from 10 to the negative 9th up to 3.75 times 10 to the negative 7th meters. Ultraviolet light, or UV light you might hear it called sometimes, this is kind of famous because it can cause sunburns. You go to the beach on a warm day, if you're exposed to too much ultraviolet light, you get sunburns. How do you protect against those? Well, sunscreen, but also the Earth's ozone layer filters out a ton of UV light. Not a lot makes it through the ozone layer, okay? Helps protect Earth from UV rays. Some does, but a lot doesn't, which is why the ozone layer is so important to help protect us from UV light, because this can actually cause sunburns, can also cause cancer. It's got enough energy to actually change your cells. And that's, as we go up here, you're going to see that we're getting more and more energetic as we go. X-rays are next, right down here. The frequency range for X-rays is 10 to the 16th up to 10 to the 20th hertz. The wavelength range is anywhere from 10 to the negative 12th to 10 to the negative 7th meters. These are obviously used by doctors to image body parts. And there's a reason that the doctor or the dentist or whoever drapes that big that big lead apron over you. X-rays are extremely high energy, and you don't want things with radiation with high energy getting near you that often, because what it can do is it can go in and it can kind of start messing with your cells. These can actually be dangerous. Matter of fact, flight attendants or anywhere that has any job that has possible exposure to radiation, you have to be really careful. Flight attendants, for one, they're up in the upper atmosphere. There's a lot of harmful radiation that gets filtered out as we go towards the ground, where we don't get a lot of it on the ground. But flight attendants, a couple miles up, they might get exposed to some of that stuff. So they actually wear their little badges that say their company. Those are actually radiation detectors. They send those in every once in a while, every few months, and it tells them, okay, how much radiation have I been exposed to? If they've been exposed to too much, they can't fly for a little while. Finally, gamma rays. These are the weird ones. Gamma rays are extremely high frequency, extremely low wavelength. The frequency range is greater than 10 to the 18th hertz. The wavelength range is less than 10 to the negative 10th meters. They are smaller than the radius of an atom. Gamma rays come from radioactive decay. Okay? When radioactive decay happens and certain types of elements change into other types, sometimes gamma rays are released. They also come from deep space. There are certain events out in space that happen that release gamma rays. Okay? These are crazy high energy. Matter of fact, they have, as you can see, an extremely short wavelength, a very high frequency, a very short period because of the high frequency, and also a very high amount of energy. I need you to understand the correlation between frequency and energy, because that's going to be very important in a few classes. Okay? These are just some real quick facts about the electromagnetic spectrum, just so you can get a handle on what type of radiation is used for what and what it does. Biggest thing here, make sure you understand that chart, how the frequency goes, in what direction frequency is bigger, in what direction wavelength is bigger. Make sure also that you can use the equation V equals F lambda. If you know the speed and you know one of these, then you can calculate the other. That's the best piece of advice I can give. We've got one more topic in waves, and then we're done.